Hi, Stu Schwartz here from MasterMathMentor.com. This is video AB09. The topic is the chain rule, and it covers the AB manuals, pages 41 through 43. Let's examine differentiation by using a new rule, which we're going to call the chain rule. We want to take the derivative of four expressions. F of x equals quantity 2x plus 5 quantity squared. F of x equals 2x plus 5 quantity cubed. F of x equals 2x plus 5 quantity to the sixth power. And f of x equals the square root of 2x plus 5. We start with f of x equals 2x plus 5 quantity squared. This is easy. We just FOIL the expression out, getting 4x squared plus 20x plus 25, and then we take the derivative of each term and get f prime of x equals 8x plus 20. A very simple problem. The expression f of x equals 2x plus 5 quantity cubed is a bit more problematic. We have to expand the expression, which means FOILing it and then multiplying it by 2x plus 5 once more. We get f of x equals 8x cubed plus 60x squared plus 150x plus 125. And now take the derivative of each term, 24x squared plus 120x plus 150. It isn't the easiest thing to do, but it certainly is possible. Examining f of x equals 2x plus 5 quantity to the sixth, we realize that it is possible to take the derivative, but the prospect of multiplying this expression out 6 times is not something that I look forward to. Again, it is possible, but not preferable. There must be another way. Finally, we have f of x equals the square root of 2x plus 5. We can write this as 2x plus 5 quantity to the 1/2 power, but we cannot expand it. And if we cannot expand it, we cannot use our power rule. So right now, we cannot take the derivative with the set of rules that we currently know. Let's see what the chain rule says. We start off with y being a differentiable function f of u. And u can be written as a function, a differentiable function g of x. If we want to take the derivative of y equals f of g of x, we can do this using the chain rule, expressing it as dy dx equals dy du times du dx. We've never thought of dy dx, dy du, du dx as being parts of fractions, numerator and denominator. But if you think of it this way, you can see that the du's on the right-hand side of the equation cancel. We can also write the chain rule as the derivative of f of g of x as f prime of g of x times g prime of x. So, to take the derivative of f of x equals 2x plus 5 quantity squared, rather than expanding the expression, we're going to use our power rule. F prime of x is equal to 2 times 2x plus 5 reduced down to the first power. But now we must use the chain rule and take the derivative of 2x plus 5, which is 2. So our final answer is f prime of x equals 4 times the quantity 2x plus 5. For f of x equals 2x plus 5 quantity cubed, again, to take the derivative, we first apply our power rule. The 3 comes in front. we take the 2x plus 5 and reduce the power down to 2, but again must remember to multiply it by the derivative of 2x plus 5, which is 2. So our final derivative is 6, quantity 2x plus 5 squared. We prefer to leave answers in factored form for reasons you will see later. So this is the final answer. The power of the chain rule really shows on f of x equals quantity 2x plus 5 to the 10th power. There's no way we would ever want to multiply that expression out. However, the derivative is 10 times 2x plus 5, reduced now to the 9th power, again multiplied by the derivative of 2x plus 5, which is 2. So our final answer is 20 times 2x plus 5, quantity to the 9th power. Number 3 reads f of x equals 1 over 2x minus 5, quantity squared. We could choose to multiply the denominator out and use the quotient rule, but let's use the chain rule instead. We write this as f of x equals 2x minus 5 to the negative 2nd power. Then to take the derivative, the negative 2 comes in front. We write the expression to the negative 3 power and then use the chain rule to multiply by 2. So the final answer is f prime of x equals negative 4 over 2x minus 5, quantity cubed. In number 4, we have f of x equals the square root of 2x minus 5. There is no choice here. We have to write the expression as 2x minus 5 to the 1/2 power. And now, using the power rule, we write f prime of x equals 1/2 2x minus 5 to the negative 1/2. But again, we must multiply by 2. The 2's cancel, and our final answer is f prime of x equals 1 over the square root of 2x minus 5. For many problems, there are more than one way of taking the derivative. For instance, if we start with f of x equals 1 over 4x minus 3, we can attack this by the quotient rule. We square the bottom, and then for the numerator we have bottom derivative of top minus top derivative of bottom, and we end up getting f prime of x equals negative 4 over 4x minus 3, quantity squared. However, we could also attack this with the power rule, writing it as f of x equals 4x minus 3, quantity to the negative 1 power. We then apply our power rule, and we get f prime of x equals negative 4x minus 3 to the negative 2 power. However, we must again multiply by the derivative of 4x minus 3, which is 4. We still get negative 4 over 4x minus 3, quantity squared. As you take more and more derivatives, you will get a sense of which way is generally easier. Let's look at 3 more problems. 7 reads f of x equals quantity 7 minus 4x squared, quantity to the 2/3 power. To take the derivative, we take the 2/3 and write the expression with a subtraction of 1 from the power, getting to the negative 1/3 power. And the chain rule says that we must multiply it by the derivative of 7 minus 4x squared, which is negative 8x. Simplifying, our answer is negative 16x over 3 times the quantity 7 minus 4x squared to the 1/3 power. Number 8 reads f of x equals negative 5 square root of x squared minus 4x plus 1. Our first step is to rewrite the expression as negative 5 times x squared minus 4x plus 1 to the 1/2 power. Taking the derivative now, we can bring the 1/2 in front, reduce the expression by 1, and then multiply by 2x minus 4, which is the chain rule. We can divide the 2 into 2x minus 4, getting x minus 2, and we're left with negative 5, quantity x minus 2 over x squared minus 4x plus 1 to the 1/2 power. Number 9 reads f of x equals negative 2 over the fourth root of 6x minus 1. Our first step is to rewrite this as negative 2 times 6x minus 1 to the negative 1/4. Note that I did not write f of x equals, I just wrote an equal sign. It is assumed that we're still talking about f of x. To take the derivative, the negative 1/4 comes in front and multiplies by negative 2 to get 1/2. 6x minus 1 to the negative 5/4. And again, the chain rule says to multiply by 6. So the final answer is f prime of x equals 3 over 6x minus 1 to the 5/4 power. Note that I do not use the convention that I established above because I would like the last step of the problem to state f prime of x equals some expression. At this point of time in the course, there are 3 algebraic forms for differentiation rules so far. Later we will develop more, but right now there are 3. We start with the power rule, which is always in the form of y is equal to some expression to a power. The product rule is in the form of y is equal to expression 1 times expression 2. And the quotient rule is in the form of a fraction, y equals expression 1 over expression 2. Some of the other basic differentiation rules that we showed in section 8 are no longer needed. For instance, the constant rule is really a specific application of the power rule. For instance, if y is equal to 9, that can be written as y equals 9x to the 0 power. And by the power rule, we can write the derivative as 0 times 9 times x to the negative 1, which is 0. The single variable rule is also a use of the power rule. We can write y is equal to x as y is equal to x raised to the first power. And therefore the derivative is 1 times x raised to the 0 power, which is 1. Finally, the constant multiple rule is a specific example of the product rule. We can write y equals 8x squared as 8 times x squared. And by the product rule, y prime is equal to 8 times the derivative of x squared, which is 2x, plus x squared times the derivative of 8, which is 0. And we end up getting y prime is equal to 16x. Students sometimes get confused by these forms. They wonder, where's the chain rule? Isn't that a basic form? And the answer is no. The chain rule is not a basic form, but it is always in effect. For example, if y is equal to 8x squared, we can write that as 8 times the quantity of x squared. By the power rule, the derivative is equal to 8 times 2x. However, we need then to multiply by the derivative of x, which is 1. And of course, we do not need to write any multiplications by 1. So the chain rule is still there working, but it's just invisible. Time for you to do some work. Stop the video and then go to pages 42 and 43 in your manuals. Look at problems 10 through 15. You are directed to find the form of the functions. You do not actually have to take the derivative, just find their forms. Number 10, f of x equals x squared times 2x minus 3 quantity to the fourth, is a product. X squared is one term, 2x minus 3 quantity to the fourth is the other term. Yes, there are powers in there, but the primary form is a product. The same is true on 11. F of x equals x square root of 4 minus x squared. X is one term, and 4 minus x squared to the 1/2 is another term. Number 12, f of x equals 2x minus 1 over 2x plus 1, quantity to the 5th power, is a power rule. The entire expression is taken to the 5th power. Yes, there is a quotient inside, but the primary rule is a power. Number 13, f of x equals x over the square root of x squared minus 1 is a quotient. There is a numerator, there's a denominator, so it's a quotient. 14, f of x equals the square root of x over 4x minus 1 would be written as x over 4x minus 1, quantity to the 1/2 power. That makes it a power rule problem. And finally, f of x equals x squared minus 4, quantity to the negative third, times x squared plus 4, quantity to the third, is a product rule. Now, it may be prudent to take the x squared minus 4 to the negative third and write it in the denominator, and therefore the problem would become a quotient rule. But the form of the problem originally is in the form of a product. We need to talk a little bit about simplification. You might have a problem in a textbook that asks you to take the derivative. You do so, and then compare your answer to the answer in the answer book, and you find that it's not the same. Did you do something wrong? And the answer is not necessarily. It may be that the form of your answer does not match the form of the answer book. So let's look at the differentiation process. You apply one of your basic rules and you get an answer. We need to multiply out any of the constants. Once you do that, we say that that is an adequate answer. It describes the derivative. However, the best answer is applying algebraic rules to get an answer in fractional form with both the numerator and denominator in factored form. When an answer is in the form where it is in a fraction and the numerator and denominator are factored, we will find later in the course that problems that use the derivative are much easier solved. However, we do not want to make this into an algebra course, as some of these simplifications take time. So for right now, we will say that the adequate answer is fine. We've already determined the forms for problems 10 through 15. As we go through the differentiation process, we will stop when we get an adequate answer, and that is in blue. I also show the work to get the best answer in red. It's up to you whether you want to look at that, and you can stop the video to examine those steps. In problem number 10, we're told that f of x equals x squared times 2x minus 3, quantity to the 4th power. We established this as a product rule. So we have x squared, the 4 comes in front, we write the expression down to the 3rd power and then use the chain rule and multiply it by 2. The second piece of the product rule gives 2x minus 3 to the 4th times the derivative of x squared, which is 2x. We do the multiplication of constants and end up getting f prime of x equals 8x squared times the quantity 2x minus 3, quantity cubed, plus 2x times quantity 2x minus 3, quantity to the 4th power. In problem 11, f of x equals x times the square root of 4 minus x squared, we have already determined this as a product rule problem. I skipped the step of writing the square root of 4 minus x squared as 4 minus x squared, quantity to the 1/2 power. So the derivative is x times 1/2 times the quantity 4 minus x squared now to the negative 1/2. And now we have to take the derivative of 4 minus x squared, which is negative 2x. The second part of the product rule is simply 4 minus x squared, quantity to the 1/2 power. Doing the few multiplications, we get f prime of x is equal to the square root of 4 minus x squared minus x squared over the square root of 4 minus x squared. In 12, we have f of x equals the quantity 2x minus 1 over 2x plus 1 to the 5th power. This is a power rule. So to take the derivative, the 5 comes in front. We write down the fraction to the 4th, and now we have to take the derivative of the fraction, which involves the quotient rule. So we have to square the 2x plus 1 quantity squared for the denominator, and the numerator is 2x plus 1 times 2 minus 2x minus 1 times 2. In that second part, the 4x's cancel, and we're simply left with 4 over 2x plus 1 quantity squared. In writing the final answer, we multiply the 5 and the 4. We have a 2x minus 1 to the 4th, but downstairs we have a 2x plus 1 to the 4th and another 2x plus 1 squared, so we get 2x plus 1 quantity to the 6th. Number 13, f of x equals x over the square root of x squared minus 1 is an ugly quotient rule. Yes, you can change it into a product rule, but you're going to end up with a lot of negative exponents that you're going to have to deal with later. Best to deal with it as a quotient. So in taking the derivative, we square the bottom, which turns out to be nice. We get an x squared minus 1. Upstairs, we get x squared minus 1 to the 1/2 times 1 minus x times the derivative of x squared minus 1 to the 1/2 power. And that involves the power rule, and we end up with 1/2 x squared minus 1 to the negative 1/2 times 2x. We now have a complex fraction, and the best way of clearing this complex fraction is simply multiplying by x squared minus 1 to the 1/2 over itself. And when we do that, magic happens. So we get the derivative is x squared minus 1 to the 1/2 times x squared minus 1 to the 1/2, which is simply x squared minus 1. And in the second multiplication, the 2's cancel, and the x squared minus 1 to the 1/2's cancel, and we're simply left with x squared. And the denominator is x squared minus 1 to the 3/2. So our final answer is the derivative is negative 1 over x squared minus 1 to the 3/2 power. No matter what, you're going to have to deal with some algebra, and that's why it's important that your algebra skills are sound. In number 14, we have f of x equals the square root of x over 4x minus 1, which we know we can write as x over 4x minus 1 quantity to the 1/2 power. This is a power rule. To take the derivative, the 1/2 comes in front. We take our fraction to the negative 1/2, and then have to take the derivative of our fraction, which involves the quotient rule. And we end up with 4x minus 1 quantity squared on the bottom, and 4x minus 1 minus 4x on top. In simplifying, I looked at the second part of this first and realized that we got negative 1 over 4x minus 1 quantity squared, and the 2 was there from the 1/2. And we also have x times 4x minus 1 to the negative 1/2. Realize that a fraction to a negative 1/2 power means that we can take the fraction and invert it and raise it to the 1/2 power. So we can change that fraction to 4x minus 1 over x to the 1/2 power. That's an adequate answer, but notice that the best answer is only one more step. Number 15, f of x equals x squared minus 4 to the negative 3 times x squared plus 4 to the third, is in the form of a product. However, at this point, we're going to take the first expression and bring it downstairs, writing it to the third power, because we can now write it as x squared plus 4 over x squared minus 4, the whole quantity to the third power. And this is now the power rule. In using the power rule, we take the 3, run it outside, and write the fraction down to the second power. We then have to take the derivative of that expression, and that's a quotient. So we end up with x squared minus 4 quantity squared on the bottom. Upstairs we get x squared minus 4 times 2x minus quantity x squared plus 4 times 2x. In the next step, we simplify that last piece and we get negative 16x over x squared minus 4 quantity squared. So putting everything into factored form, because it's only one more step, we end up getting f prime of x is equal to negative 48x, x squared plus 4 quantity squared, over x squared minus 4 to the fourth power. Again, some algebra is needed here to get these in the form that we would like it to be. Sometimes differentiation problems can be constructed that minimizes the algebra and just concentrates on the calculus. This type of problem is shown here. We are given two functions, f and g. We're told that f of 2 is negative 3 and f prime of 2 is 6. We're also told that g of 2 is 3 and g prime of 2 is negative 2. We're also told that f prime of 3 is 4 and g prime of negative 3 equals negative 1. And you're asked to find h prime of 2, where the problems given will define h. In 16, you're told that h of x is equal to f of x to the third power. So, to take the derivative, this is a power rule. We bring the 3 in front, write the expression down to the second power, and then take the derivative of what's inside that brackets, which is f prime of x. At this point, we plug in the 2. So h prime of 2 is equal to 3, f of 2 squared times f prime of 2. At this point, we go to our chart above and fill in the information. So we get 3 times negative 3 squared times 6, and our answer that h prime of 2 is equal to 162. In 17, we're told that h of x is equal to the quantity f of x minus g of x quantity squared. This again is a power rule, so to take the derivative, the 2 comes in front. We write the brackets down to the first power, but then need to take the derivative of what's inside those brackets. The derivative of f is f prime, and the derivative of g is g prime. So we now plug in the 2, and we get 2 times the quantity f of 2 minus g of 2 times the quantity f prime of 2 minus g prime of 2. At this point, go up to your chart above and fill in the information, and your answer is h prime of 2 equals negative 96. In 18, we're told that h of x is equal to the square root of 4g of x minus 1. And we know that we can write that to the 1/2 power. So taking the derivative, the 1/2 comes in front, and we write that expression to the negative 1/2 power, and I skipped a step and already put it into the denominator. But we then have to use the chain rule and multiply by the derivative of what's inside the square root, which is 4g prime of x minus 1. At this point, plug in the 2, and at this point, you can go to your chart, fill in all the proper information, and your answer is negative 3/2. Number 19 reads h of x is equal to f of g of x. This is called the composite function. and sometimes students get confused over it. The derivative of f of something is f prime of that something times the derivative of that something. So h prime of x is f prime of g of x times g prime of x. Now when we plug in the 2, we get f prime of g of 2 times g prime of 2. Now again, we have to be careful here. Okay, g of 2 is 3, g prime of 2 is negative 2. So f prime of 3 times negative 2 by the table is 4 times negative 2, which is negative 8. 20 is similar. It reads g of f of x. So the derivative of g of an expression is g prime of the expression times the derivative of the expression, or g prime of f of x times f prime of x. Plugging in the 2, we get g prime of f of 2 times f prime of 2. Since f of 2 is negative 3 and f prime of 2 is 6, we get g prime of negative 3 times 6. And g prime of negative 3 is negative 1 times 6 is negative 6. Finally, 21 is f of negative f of x. Again, this is a composite function, and the derivative is f prime of negative x times the derivative of what's inside that parentheses, which is negative f prime of x. So this becomes f prime of negative f of 2 times negative f prime of 2. Have to be careful with the negative signs. So we end up with f prime of 3 times negative 6. Since f prime of 3 is 4, our answer is negative 24. The testers on the AP exam love these types of problems in multiple choice because there are so many mistakes that students can make.